Hey, what's up everyone? My name is Costa and I am a machine learning engineer intern at Weights and Biases. I'm also a fourth-year PhD student at Drexel University specializing in reinforcement learning. Today I want to talk about Proximal Policy Optimization, or PPO. PPO is a deep reinforcement learning algorithm proposed by OpenAI in 2017, and it has since become one of the most popular reinforcement learning algorithms. In today's video, we will build a PPO implementation in PyTorch from scratch, covering 11 general implementation details. You can find out where these implementation details come from by clicking on the GitHub permanent links in my blog post, which is linked in the video description. At the end of this video, you'll know how to train the agents to balance a carpool with PPO, which is only a start. In the follow-up videos, we will make it work with a variety of games by making small modifications to today's implementation. The target audience of this video is intermediate to advanced reinforcement learning practitioners who are familiar with PyTorch and roughly how PPO works. If you're a beginner, a good way to start with PyTorch is to read the official tutorials. My personal favorite is the 16-minute blitz, which dives into the basics such as tensors and automatic differentiation before talking about the more advanced neural network stuff. To read more on RL and PPO, I highly recommend checking out Joshua Akiem's OpenAI Spinning Up, which is a very beginner-friendly educational resource. For more intrigued readers, the Policy Gradient Algorithms blog post from Leo's Log is also a fantastic resource. The first part of this video is logistics setup on quality of life developer tools such as ArcParse, Tensorboard, and Weights and Biases, so feel free to jump to the following timestamp when the implementation details actually start. Without further ado, let's get started. We will first set up the development environment. For my personal workflow, I usually use PyM to set up the virtualized environment, set up Poetry as the package manager, and then use Poetry to install all of my dependencies. After the installation has finished, we will start by creating a Python file. Our first step is to use the ArcParse package to set up some common variables. I usually give each variable a name, a type, a default value, and a help text for documentation. My first common variable is the experiment name, which by default takes on the value of the file name. Then I have the gem ID, and by default I set it to carpool v1. Here I have the learning rate, and by default I set it to 2.5 e-4. Then I set up a random seed and by default set it to 1. Next, we have the total time steps, which is the number of environment steps, and by default we set it to 25,000. Then I have two GPU related variables. The torch deterministic equals true will help us reproduce the experiments, and the CUDA equals true will utilize GPU whenever possible. We can then parse these variables or command line arguments and print to see their values. This is really helpful because if we want to change one configuration, we can just do this in the command line without changing the code at all. Next, we're going to set up Tensorboard. Tensorboard is a visualization toolkit to help you visualize training losses or episodic returns. Let's import the Tensorboard summary writer, set up a unique run name for our experiment, and save the metrics of our experiment to a folder with that run name. To test it out, we're going to encode our args variable as a text data, and we're also going to add some scalar data. We can now run the script and launch Tensorboard to see the recorded metrics. We can open Tensorboard's dashboard by clicking on the URL here. Here I can see my test scalar data, I can zoom it in, tune the smoothing parameter. I can also go to the text section to see everything in the args parameter as my hyperparameters. Next, we're going to set up Weights and Biases, which is a developer tool that helps track everything related to our experiments in the cloud. To add weights and biases, we're going to set up a track flag that when toggled will log our experiments to weights and biases. Then we set up a WMB project name that defaults to cleanRL. Then we also set up a WMB entity. By setting it to none over here, WMB will use my default entity, which is my username. To use weights and biases, we simply add a block of code under the track flag, which sets up an experiment with WMB in it. Here we add our default project name, our default entity, tell WMB to sync our Tensorboard metrics, add our args variable as a configuration, add the run name, tell WMB to upload the videos in the gym environment, and finally save a copy of the code. Because we use Tensorboard and the track flag, our code is still be able to run locally, but whenever we need it, we can turn on the track flag and all of a sudden, we get experiment tracking for free. That is to do Python ppl-track. This will finish in just a second, and we can go to this URL to see the tracked experiment. Once we get into the URL, we can see our test logs, zoom it in, smooth it, and we can also go to the Overview tab to see metadata and our hyperparameters. We can go to the Files tab and open the requirements.txt to see the log dependency, and we can also see a copy of our code here. Our final logistics is to delete the test code and set up random seeds. Specifically, we import random numpy torch and then set up their random seed over here. For PyTorch, we also set up a device variable that's going to try to use GPU if CUDA is available, and we specifically set the CUDA flag to be true. Now we're ready to dive into the implementation details. Detail number 1. PPO deals with what's called the vector environments, which stacks multiple independent environments into a single environment. You might have already seen code like this to work with the gym environment. Roughly how it works is you use gym.make to initialize the environment, reset the environment to get the first observation, sample an action to step the environment, which gives you the next observation, the current reward, a done variable that tells you whether the episode has finished or not, and finally an info for extra stuff. Once the episode is finished, you will use m.reset to get the observation for the next episode. Oftentimes, people will set up a variable to record the episodic return, as shown here. This code is straightforward and would run just fine. A quick engineering tip is to use a record episode statistics gym wrapper to record the episodic return instead. When an episode is finished, this wrapper will populate the info variable with the episodic return. We can do a quick verification by running the code, and we will see duplicate episodic return being printed. Now we can remove the code that self-manages episodic return for clarity. Another quick tip is to use a record video wrapper to record the videos of the agents playing the game, which is always helpful for debugging what the agent is actually doing. It's very important to note that PPO deals with the vector environments instead of deal with gym environments directly. To use the vector environments, we will first create a function that returns a function that creates a gym environment. Then we can use gym's synced vector env API to create a vector environment by passing a list of env creating functions. The vector environments API is very familiar. We will still use m.reset to get the initial observation and then sample an action to step the environment. What's changed is the vector environments will automatically reset. Once the episode is finished, the step function will discard the terminal observation from the current episode and return the initial observation from the next episode. This code would also just run fine. It's worth mentioning that since we're using the gym integration with weights and biases via monitor gym equal to true, when we turn on experiment tracking, the videos of the agents playing the game will automatically be logged to weights and biases. Here, I can use a friendly slider to visualize what the agent is actually doing at different stages of training. In practice, I'll set up the makeEnv function a little bit differently. I will include a capture video flag to allow me to record videos for only the first sub-environment. I will also add a section for the random seeds to make things more reproducible. I'll add a capture video flag in my args variable. I'll also set up a numenvs variable to tune the number of sub-environments in the vector environment. Then I'll pass in the relevant variables to the makeEnv function and use this args.numenvs variable to tune the number of env creating functions. Now let us clean up the demo code we had earlier. Before we continue, we're going to assert the script only works with discrete action space. Also, we're going to print out some useful ends properties. As we can see, Carpool's observation space has 4 features and its action space has 2 discrete actions, going left and right, respectively. At this point, we're ready for something more interesting. We're going to set up the agent class and code up the neural network. Let us import some packages, including Torch's neural network module, optimizer module, and a categorical distribution. Then set up an agent class that takes em's as the argument. The second implementation detail is the orthogonal and constant initialization for the layer's parameters. Here, I will create a layer init function that takes a layer and two initialization parameters as inputs. PPO uses the orthogonal initialization on the layer's weight and the constant initialization on the layer's bias, whereas PyTorch would use different layer initialization methods. Now we're going to set up the critics network, which is composed of 3 linear layers with the hyperbolic tangent as the activation function. Notice the layers by default uses square root of 2 as the standard deviation or gain for the orthogonal initialization, but the output linear layer uses 1 as the standard deviation. Another thing to note is the input shape to the first linear layer is the product of the observation space shape. In this case, the input shape is the product of this tuple, which is 4. The actors network has a similar setup, except its output linear layer is initialized with a different standard deviation of 0.01. Such standard deviation ensures the layer's parameters will have similar scalar values, and as a result, the probability of taking each action will be similar. Another difference is the number of output features is the same as the number of available actions in the action space, which is 2. In comparison, the number of output features in the critics output layer is just 1. We can now create an instance of the agent class and print it out to see what it looks like. Nothing too surprising over here. The third implementation detail is to set up the atom's epsilon parameter correctly. By default, PyTorch's atom optimizer has epsilon parameter to be 1e-8. However, the original implementation uses epsilon equals 1e-5. Here, we create the atom optimizer with respect to the agent's parameters, set up the learning rate, and match the epsilon parameter of 1e-5. Our next step is to understand the training loop and subsequently set up the storage variables. On a high level, we'll take the agent we just initialized to do policy rollouts, aka to play the game. This generates rollouts data that we can use for policy training. After which, we can take the updated agents to do policy rollouts and continue the training loop. But how much rollouts data do we collect? This leads to the introduction of a very important variable called numSteps. This numSteps variable controls exactly how much data we want to collect. For example, here I have numSteps set to 128 and numM set to 4. That means for each policy rollout, I will collect 4 times 128 equals 512 data points for training. These data points include the observations, actions, log probabilities, rewards, dones, and values. And notice how we set up the shapes to capture these 512 data points in these variables. Also, we'll set up a global step to track the number of environment steps, a start time that will help us calculate frames per second later, a next obs to store the initial observation, and a next done to store the initial termination condition to be false. If you recall, our rollouts data has 512 data points. This 512 is also known as the batch size. Here, we simply create a variable to store it. Given this, if we divide the total time steps by the batch size, we can actually calculate the number of iterations or updates for the entirety of training. Given our current settings, we have 48 updates. Now that we have the initial observation, we're going to implement the critics inference by passing the observation to the critics network. Then we're going to try out this getValue function. Here, I see my initial observation has shape 4, 4, where the first 4 is the number of environments and the second 4 is the observation space shape. And when we do agent.getValue next ops, we get 4 scalar values for each environment. And its shape is simply 4, 1. When doing the actors inference, it's actually best to bundle the results with the critics inference. So here I would create a getAction and value function. Then I would pass in the observation X to the actors network to get the logits, which are unnormalized action probabilities. The logits are then passed to a categorical distribution, which is essentially a softmax operation to get the action probability distribution. And since we're in the rollout phase, we're going to sample actions. Finally, we're going to return the actions, the log probabilities, the entropies, and the values. Let's test out this function by giving it a run. Here we see the sampled actions, the log probabilities associated with these actions, the entropies of the action probability distribution, and the values. Let us clean up these print statements real quick. Now we can set up the training loop based on the nums updates. At this point, we introduce the fourth implementation detail. The learning rate is annealed with each update. We implement this by setting up an anneal LR flag and by default set it to true. Then we will get the current learning rate by multiplying the learning rate with a fraction variable. This fraction variable is 1 at the first update and will linearly decrease to 0 at the end of the updates. Finally, we will use PyTorch's API to update the learning rate. Note that each update corresponds to one iteration of the training loop. The policy rollout is itself a loop, which is implemented as an inner loop with a range of num steps. Because each policy step happens at the vector environment, we increment the global step by the number of n's. Then here we store the next observation and next done to the storage variables. During the rollouts, we don't need to cache any gradient, so we can get the action, log probabilities, and values under the torch.nograd context. We will also need to put them in the storage variables. Then we can step the environments. Here, I transfer the actions from the GPU to CPU to do the step. I also need to transfer the returned rewards to GPU, and so do the next obs and next done. Lastly, we can use Tensorboard to log the episodic return and length as shown earlier. We'll give it a quick run, and as we can see, the script would print out every episodic return. And at the end of the script, the global step will match the total time steps of 25,000. The fifth implementation detail is PPO uses General Advantage Estimation or GAE to do advantage calculations. Let us set up a GAE flag and by default set it to true. Then we introduce a discount variable gamma and set it to 0.99. We also set up the lambda variable for GAE and set it to 0.95. To implement GAE, here I have copied the modified code from the original repo. It's a very intricate implementation, especially compared to the formulas in the original paper. Feel free to write out a few terms on a piece of paper to help with understanding. For comparison, the common way to do advantage calculation is to use returns minus values. One worth mentioning detail is PPO bootstraps values if the environments are not done. In this example, all 4 environments are not done, and we estimate the values of the next obs as the end of rollout values. Another detail is returns is calculated as advantages plus values, which is different from the regular return calculated as sum of discounted rewards. Here, I'm using my IDE Spider to easily inspect the values of various variables, and I can directly show the regular returns is different from the returns from GAE. One more thing, we're going to create variables to store the flattened storage variables. Here I have 512 data points, which is the batch size. The sixth implementation detail is PPO will break this batch of 512 data into mini-batches for training. To do so, let us introduce a new variable to tune the number of mini-batches. And by default, we set it to 4. And the mini-batch size is batch size divided by the number of mini-batches. We also set up the number of update epochs and by default set it to 4. To do training, we acquire all of the indices of the batch, and for each update epoch, we shuffle these batch indices. Afterwards, we would loop through the entire batch, one mini-batch at a time, where each mini-batch indices contains 128 items of the randomized batch indices. Given this, our training finally begins. We first do a forward pass on the mini-batch observations. Notice we also pass in the mini-batch actions so that our agent would not sample any new actions. This forward pass gives us the log probability, entropy, and value. We can then do a logarithmic subtraction between the new log probabilities and the old log probabilities associated with the actions in the policy rollout phase. This gives us the log ratio, and we can use the exponential function to get the ratio. Something we should know is during the forward pass of the first mini-batch, this ratio would contain only ones. That is because we haven't made any change to the policy parameters, and therefore the new and old log probabilities would be the same. The seventh implementation detail is PPO does advantage normalization. In addition to acquiring the mini-batch advantages, we set up another flag to do advantage normalization and by default set it to true. And the normalization is done by subtracting the mean and divided by the standard deviation plus a small scalar value to prevent the divide by zero error. The eighth implementation detail is PPO's clipped policy objective. To implement it, we set up a clip coefficient and by default set it to 0.2. Then we set up the policy loss as follows. Notice the policy loss does the max of negatives and the paper's objective does the min of positives, so they are equivalent. The ninth implementation detail is PPO also does value loss clipping. Here we add another flag to do value loss clipping and by default set it to true. Then we implement the value loss as follows. Normally, the value loss is implemented as a mean squared error between the predicted values and the empirical returns, but the original implementation also does clipping like the clipped policy objective. The 10th implementation detail is PPO also includes an entropy loss in its overall loss. Here I add a coefficient for the entropy loss and by default set it to 0.01. I also set up a value loss coefficient and by default set it to 0.5. Then the overall loss is implemented as follows. The idea is to minimize the policy loss and the value loss, but maximize the entropy loss. Entropy is a measure of the level of chaos in the action probability distribution. Intuitively, maximizing entropy would encourage agent to explore more. Our final implementation detail is global gradient clipping. Here we set up a maximum gradient norm and by default set it to 0.5. Normally we would implement the backpropagation like this, but this implementation detail would add this line of code. The original implementation also has variables to help debug. For example, the callback light-blur divergence helps us understand how aggressively the policy updates. The original implementation approximates the KL divergence by doing negative log ratio. However, a recent blog post from John Schulman suggests the following approximation is a better estimator. There is also a clipped fraction variable that measures how often the clipped objective is actually triggered. Another variable is the explained variance, which tells you if your value function is a good indicator of the returns. A bonus implementation detail is what's called early stopping. This is actually an implementation detail proposed by Joshua A. Kim in the OpenAI Spinning Up. The rough idea is to stop the policy update if the KL divergence has grown too large so as to exceed a preset target KL divergence threshold. To implement it, we set up a target KL variable and by default set it to none. If you want to consistently use it, you can also set it to 0.015, which is the default value in OpenAI Spinning Up. However, by default, let's turn it back to none. And here we add a condition to break the update epochs if the approximate KL divergence go over that threshold. Notice here we're implementing the early stopping at the batch level. However, it is also possible to implement it at the mini batch level. The OpenAI Spinning Up's PPO implementation didn't really use a mini batch, so this detail is really up to us. Finally, we'll use Tensorboard to record all of the metrics. It's now time to give it a run. By clicking on the generated WMB link, we would go to this page. Immediately, we see the videos of the agents playing the game, and we can adjust the slider to see the agent's behavior at different stages of the training. Then, if we scroll down and expand the loss section, we can see the various losses. And if we go down to expand the chart section, we see the episodic returns and episodic lengths. We can also go to the Overview tab, and here we see all of our hyperparameters. Scrolling up, we see our experiment took 18 seconds to finish, and here we can see the exact command that was used to produce its experiment. We can also go to this tab to check out the system metrics usage. And because our experiment has finished so fast, there isn't really that many data points. We can also go to the Files tab and check out the requirements.txt for all of the logged dependencies. And finally, we can go to the Code tab to see a copy of our code. This concludes our video. Thanks so much for watching. If you have any questions, feel free to comment down below. I also encourage you to check out the links in the video description where you can find my source code and a blog post on the implementation details. Thank you, and I'll see you in the next video.